Hey everybody, this is 3M gravitational fields. So they say the mass of Mars is 1/10 times that of Earth, and the diameter of Mars is 1/2 that of Earth. And that's just some useful information that we're going to use in this next parts here. So part A, derive the equation for the gravitational, in other words, G, it should say gravitational attraction, gravitational acceleration, G, due to a planet here. So let's write down what we know. We know that a force is equal to mass times acceleration. Now, there's only one force on something free falling, and that is the force of gravity. So the force of gravity is equal to mass times acceleration. But this force of gravity we're talking about here, we got to show why it simplifies down just to mg. How do we get g, little lowercase g, in the first place? This force of gravity has to be Newton's universal law of gravity. So then we can say that this force of gravity is the universal gravitational constant times mass 1, let's pretend that's the planet, times mass 2, let's say that's the falling object like the apple, over the distance between their centers squared. And this would be the falling apple here. So that would be mass 2 times its acceleration. Well, look, the apple's mass, let's say, is on each side, so it cancels out. So then if I rewrite it in terms of this A, which is now what we're calling G, this gravitational acceleration here is equal to big G times the mass of the planet, I'll write it big there to indicate that, times the radius, or divided by the radius of that planet squared. So this is how we find the gravitational acceleration of any planet. And this, by the way, goes for the apple as well. It's just the apple has such a small mass that its acceleration due to gravity is basically 0. So the reason G is 9.8, roughly 10 on Earth, is if you took the universal gravitational constant times the mass of the Earth, divided by the radius of the Earth squared, you'd get 9.8. So next thing they say in part B here is let G be the gravitational field strength on Earth's surface, derive an expression for the gravitational field on the surface of Mars without plugging in the value for the mass or the radius of Mars. Your answer should be a number multiplied by G. For each line of the derivation, explain what was done mathematically. In other words, annotate your derivation. Well, I'll just explain that part here. So let's start with this. Here is the G that we're working with. So since we're doing a proportional reasoning question here, let's say this. G is proportional to the mass of the planet divided by the radius of the planet squared. And that is always true everywhere in the universe. So let's plug in what we did for each of these. So in this case here, the mass is 1/10. So we have 1/10 the mass of Earth up here. And then the radius, it says, is 1/2. So we have 1/2 the radius, but don't forget that we square that. So then in the next part there, what we are going to do is realize that, and this mass is the Earth, and this is the radius of Earth, so it would still be proportional to G there. So we get 1/10, that's the important number, and then the 1/2 squared is 1/4. But you're dividing by 1/4, so when you bring it back up to the top, you get 4/10 overall, or in other words, you get 2/5 of G here on Earth. So if G is roughly 10, then you're talking about 4 meters per second squared on Mars there. So the next question here, part C, says a rock is dropped 2 meters above the surface of the Earth on Mars. Does this rock take a longer or shorter time to fall than a rock dropped 2 meters above the surface on Earth? Justify your answer without using equations. Well, we have less acceleration on Mars. So if you're falling the same distance and we have the same starting velocity, which is 0, then less G means more time, right? We're accelerating at a slower rate there. Part D says, on the internet, a student finds the following equation for the time an object will take to fall to the ground from a height h, dependent upon the mass and radius of a planet it is on. T equals the square root of 2 times h times the universal gravitational constant divided by the mass and radius squared. Regardless of whether this equation is correct, does it agree with your qualitative reasoning in part C? So if we look here in part C up here, we said that because our mass is smaller and our radius is smaller, but both of those in the denominator. So if we divide by a smaller number, then if these are smaller, then the time will get bigger. So yes, it does agree with what we were saying in part C up here. So next part E here, they say another student deriving an equation for the time it takes for an object to fall from a height h makes a mistake and comes up with t equals the square root of r squared divided by 2gmh. Without deriving the correct equation, how can you tell this equation is not plausible? In other words, that it does not make physical sense. So the big thing here is look where h is. H is down here. What this would say is h gets bigger and bigger and bigger. So you're falling from a bigger and bigger height. Since you're dividing by that number, you're dividing by a bigger and bigger number, t is proportional to the inverse of 1 over h. So a bigger h would make the time smaller. That doesn't make any sense. That can't be. Makes no sense. And that's the reason that that definitely can't be a correct equation.